Okay, so today we're going to start chapter 7, and it really focuses on sequences and series. And today we're just going to kind of talk about what some of those mean and what those words mean there. So a sequence is a function which computes an ordered list. So it's literally plug in a number, get out a number. So our n's are what we plug in. So we always start with n equals 1. 1 plus 5 gives me 6. So the function n plus 5 generates 6, 7, 8, 9. 1 plus 5 is 6. 2 plus 5 is 7. 3 plus 5 is 8, and so forth. And this could keep going on for as long as we want our domain to be, or it could be infinite and go on forever. A finite sequence is that. It's finite. It ends. Okay, and it deals with a set of the natural numbers. So not all the natural numbers. If you remember, natural numbers are your counting numbers. So starting with 1. So I could have a function be f of n equals n, where my domain is just n. It goes from 1 to 12. Okay, so if I did that for the one above, this list would not go on forever. It would just go until n was 12, which 12 plus 5 would give me 17. So my generate 6 when n is 1, when n is 2 is a 7, when n is 3 is an 8, and eventually when we get to n is 12, it would come out with a 17. And that would be my finite sequence. An infinite sequence is just that. It goes on forever. Okay, it deals with the entire set of the natural numbers. So let's say we deal with the natural numbers being multiplied by 2. So the function of 2n. So when n is 1, we get out of 2. When n is 2, we get out of 4. N is 3, we get out of 6. N is 4, we get out of 8. And that would go on forever. Because we're dealing with all the natural numbers, and that's all your counted numbers, and we can keep counting forever. Some important notation in terms. You'll see this, a with a little subscript 1. We say that as a sub 1. That just means the first term in a sequence. A sub 2 just means the second term. And any little number I put there just means that term of the sequence. And then when we say a sub n, that is your nth term or our general term. So here's the first example. Write the first 5 terms of this sequence. So what they mean is they want to know what is a1, what is a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. Okay, sometimes you might need to do the work for every single one of these. Sometimes the pattern might become pretty clear quickly. So the first one, -1 to the n plus 1. So our n here is 1. So 1 plus 1 times n squared, so 1 squared. -1 squared is 1, 1 squared is 1, that gives us 1. When n is 2, okay, we're going to have -1 to the 2 plus 1 times 2 squared. So -1 to the third is a -1, and 2 squared is 4, so we end up with -4 here. Maybe go on to where n is 3, -1 to the 3 plus 1 times 3 squared. 3 squared is going to give us 9, and that -1 becomes positive, so it's 9. Go on to the fourth. You might have caught on to what this pattern might be. -1 to the fifth is going to be a -1 times 4 squared, 16, but it's going to be a -16. And if you caught on, all we're doing is going through our perfect squares. And they're alternating positive and negative because that -1 sometimes becomes a positive 1, sometimes a -1. So if you catch on the pattern, you're more than welcome to use that to help you find the rest of the series. Or sorry, the rest of the sequence. An infinite sequence, which approaches a real number, is called a convergent sequence. Okay, so in this case, this function, a sub 1 would be 1 over 1, which is 1. A sub 2, 1 over 2, which is 1/2. And then a sub 3, and this would keep going on. And if you notice, these numbers keep getting smaller and smaller. Okay. And this would be approaching what is 0. And now we don't really use the a sub infinity at all, but it's just the idea of eventually we get to some really large number there, and we talk about when we talk about limits. So the limit as n goes to infinity of this function would go to 0. So this would be a convergent sequence. It is approaching a real number. And then the opposite of that is divergent, which means it's not converging to any number. Okay, we have 1, 2, 3, 4, and then it would be 5, 6, 7. It's not going anywhere. These numbers are just getting larger and larger and not converging to anything. Our next thing we have is a recursive sequence, and the recursive definition is a sequence where one term is defined using a previous term or terms. A very famous one of these is the Fibonacci sequence. Okay, the Fibonacci sequence is based on adding the two previous numbers. So in a Fibonacci sequence, the initial term is 1, the second term is 1 as well, and to find your third term, you add those together. 1 plus 1 is 2. Then to find your fourth term, it's the second and the third term together. And then to find your fifth term, it's 2, the third and fourth. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. And that has what a recursive form of a sub n, is equal to a sub n minus 1 plus a sub n minus 2, the two previous terms. So let's find the first four terms of the sequence here. And they give us the first one. You're going to need that. So if I want to find the second one, following this here, a sub n, so a sub 2 is equal to a sub n minus 1. So 2 minus 1 is 1 plus 2n. So that would be equal to 5 plus 2 times 2, which is 9. So then a sub 3 would be a sub 2, which was 9, plus 2 times 3. 9 plus 6, 15. And then a sub 4, we're going back using our previous term, plus 2 times n. 15 plus 23, or plus 8 is 23. So we list that as 5, 9, 15, 23. And that can keep going on, but they just asked for the first four terms. The last part here is writing an explicit expression for the nth term. So we want to write an expression that would help you find any term in that sequence. So basically what we're trying to say is, how do you find the nth term? And we're always beginning where n equals 1. So you're basically looking at this is n equals 1. This one is n equals 2. Then 3, 4, and 5. So you got to look at what's going on. Well, if we look at the top part, how does 1 become 1? How does 2 become 4? How does n equals 3 become 9? Well, that's just squaring that. So on top, we just have n squared. Now if we look at the bottom, how does 1 compare to 2? 2 to 3, 3 to 4. You notice they're always 1 bigger than n. So on the bottom, we would have n plus 1. And we can test it out. Does it fit for this one here where n is 5? Well, 5 squared is 25. 5 plus 1 is 6. So this would be our explicit expression to find the nth term of the given sequence. How about you go ahead and try that last one, pause the video, and then come back here to check it out. Okay, this last one, again, you have, this is n is 1, n is 2, 3, and 4. What you do notice in common is there's always a 1 on top. So let's start with that. On the bottom, okay, we have a 2. Well, we start out with 1/2. And then somehow from 1/2, we make it a 1/4. And then we make it a 1/8. Well, if you notice, we just keep multiplying that bottom by 2. Well, this is 2. This would be 2 times 2, 2 times 2 times 2, and so forth. So really we're looking at 2 to some exponent. Well, this would be 2 to the first, 2 to the second, 2 to the third. Oh, well, you notice those exponents match what n is. So on the bottom I'd have 2 to the n. Now the one thing we do need to look out for is this alternating negative sign. Well, I have two ways to do this. I could make this a -1 and raise this to the n. So n to the 1 would make it -1. When n is 2, it would be squared, so it would be positive. So that's going to fit there. Or I could write this as 1 over 2, -1 over 2, and raise this all to the n. So if I plug a 1 in there, it does give me -1/2. Plug a 2 in there, it gives a positive, and the bottom becomes 4. Plug a 3 in there. Okay, -1/2 times -1/2 times 1/2 would be -1/8. So either of these can be used to find the nth